There we go. Alrighty, folks. So as I mentioned in my, well, I think towards the end of the last class and perhaps on Canvas, today what we're going to do is we're going to wrap up the theory and the material for this chapter all about state space realization. And we'll see how long that takes us. But then you can use the rest of the time to get started on that homework. So the homework I just posted is going to be due a week from today. You can get that going. And at that point, as usual, you can feel free to work in groups. Before that, yeah, we just have a couple of things to wrap up in terms of theory, and I'll go over a couple of we'll go over a couple of examples together. So that's the plan. That's what we're doing this time around. And of course, those of you that are in the Thursday lab section, you can, yeah, I guess I'll see you as well this afternoon. So without further ado, I'm going to go into my notes, and we'll start exploring this right here. Okay. So if you remember, this was the last question that we left off with at the end of the last class. Can we go? So if we've got a system where we're given a transfer function, can we go from a transfer function to its state space version? So, I'll say, as I recall, just to provide some context, this is the same physical system, right? It's the same physical system. So that's, there's nothing different there. Recall also, however, some of the qualities. So that state space was an internal description, which was all based on the idea of states and how those states evolved. In addition to that, it had that output equation as well. And then you had this transfer function being an input-output relationship, right? Where it was just output divided by input in the frequency domain. We also saw that we did have some procedures. So to go from state space to transfer function, that we know how to do. We do that C Si minus A inverse B plus D. And so that's one way to do it. But we also saw that there's multiple state space realizations. So you could have a state space, I don't know, 1, you could have state space 2, state space 3. So various, each with their A, B, C, D, maybe this is a slightly different A, B, C, D, this is a slightly different A, B, C, D, and that they would all correspond to the same transfer function as long as you were dealing with the same physical system. So remember which A, B, C, D you got, that would be depending on how you selected those states. So if you chose, and the examples that we saw, X1 and X2 were the voltage in the capacitor and the current of an inductor, and they led us to a certain A, B, C, D. Well, if you had chosen them in a different order or chosen other variables, you would have had other A, B, C, D realizations. However, they would all lead you to the same transfer function. So knowing all of this, what do you guys think? Can I go from transfer function to state space? So it seems like there's some reasons that, maybe yes, maybe no. So give me yeah.
I'm gonna give my argument and say most likely no, just because how is it supposed to differentiate between the different possible state spaces and like the different variables you can choose to make those state spaces with? If you have one transfer function that could come from all those different inputs.
That's a totally valid point. So I appreciate that that perspective of okay, yeah, like if I'm here, yeah, how do I know yeah, whether I came from this one or came from this one or yeah. So and I think adding to what Quinn suggested there, well, this we know, well, each of these has an input, a relationship between input and output, sure, but more so it's got this internal description. So if this is only input output, yeah, I mean, it seems difficult to go in this direction. That's a great point. So some really good arguments that from Quinn. Do I have anybody that disagrees that says, you know what? Wait a minute. I think we can do this. Like there's got to be some way that we can pull it off. Or does everybody agree that it's I guess yeah, type into the chat if you're like, you know what, even if you're not 100 convinced, but you're like, I've got a feeling this is possible. I just yeah, I want to see if there's any of you that think it could be done. Okay, so far I'm not seeing anybody chiming in the chat. Thomas says he's not sure. Jackson Rhodes says, considering how lab yesterday, yes, it's possible to do it. Scott says, yeah, I think it can be. So yeah, Jackson Rhodes, you've seen MATLAB do it, right? You you told MATLAB, hey, can we do transfer function to state space? And MATLAB gave you some ABCDs there. So unless MATLAB was absolutely cheating and BSing you, then you would think that yes, you can. And I mean, I wouldn't put that past MATLAB. It's possible that it was doing that, but I think this time around it was hopefully legit. So turns out that it is possible, and this is not the most intuitive thing based on everything that we just discussed from Quinn's comments and all these issues. But you can go from this one to one of these. That's the thing. So basically, you can't, from the transfer function, generate all these A, B, C, Ds, all these different versions before, but you can select one specific one and generate that. So it turns out, turns out that going from transfer function to state space is possible. But with that caveat, so I'll say, let's say, but, let's say to a specific state space. So to a specific state space, let's say representation or realization. So it might not be that from this transfer function you can generate just about any of them, but you can generate something that's an ABCD form, and it's going to be one of these. So how do we do this? What do I mean by this this specific one? Well, we do something called the canonical form. So that's the one that we can generate. So let's look at how we do it. So let's do TF to SS in canonical form. Okay. So basically from my transfer function, I can do one specific ABCD, and perhaps the easiest way to illustrate it is via setting a kind of a generic transfer function. So I'll show you how you build your ABCD based off of that. So let's say that I have a transfer function that looks like this. let's say my y of s over r of s is equal to the following. So this is my transfer function. And let's say in my numerator, I've got, let's make it b3 s cubed plus b2 s squared plus b1s plus b0. So that's what I've got in my top. Okay. And at the bottom, I'll do s to the fourth plus a3 s cubed plus a2 s squared plus a1s plus a0. Okay, so I've got that transfer function right there. Notice it's an order 4 system. And it's order 4 because I look at that highest exponent in my denominator. So the fact that it's order 4 suggests to me that I'm going to need an x1, x2, x3, x4, and that I'm going to have an A matrix that's 4 by 4. So indeed, that's the first thing that we can say is like, okay, this is of order 4. So let's build, I'll say from here, I'll say the state space realization is going to look like this. So let's do x1, x2, x3, x4. And remember the state space realization, the first, well, yeah, the first time you see these, it's with the derivative, right? So it's going to be the derivatives of the states. Then it's going to be a 4 by 4 matrix right here times x1, x2, x3, x4. Okay. Then plus, here you would have that column. So it would be that column like this times r of t. Okay, so that's, this here is going to be our A matrix. This here is going to be our B matrix. Now let's, yeah, scroll down just a bit and set up my y equation. So here I would have y of t. Then I would have my C matrix, which is going to be a row vector, again, of 4 entries. Then times x1, x2, x3, x4 over here. And then plus, if you guys remember, it was plus a 1 by 1 matrix times r of t. And this is my C, and this is my D. All right, so we've got, just to get us started, again, we've got everything of the right dimensions. So now it's a matter of, based off of this transfer function, can I plug in different things here so that I can always get an A, B, C, D that's correct and corresponds to the same system. So it turns out that there's a pretty structured way to do this, and it's a bit of a recipe. So the first thing is matrices B and D are actually going to be the easiest one. So actually the easiest one is D for the canonical form. So this is the only one we can do, the only one we can pull off systematically is this canonical form. And the D matrix is always 0. So this one always goes away. There's going to be nothing at all there. So for this one, yeah, you can even just get rid of it like that. So it's going to be 0 all the time. For the B matrix, it's always going to be all zeros and then 1. So over here, 0, 0, 0, 1. That's what that's going to look like. If it were a 10 by 10 matrix here, you would have 9 zeros and then a 1. That's just how that one is going to go. Okay. So those two were pretty easy. And now it's like, okay, how do these different parameters come in? So these right here, the B's are going to show up in, or the terms for your coefficients for your numerator show up here. So they're going to show up in this order. So they're going to be B0, B1, B2, and B3. So those coefficients from your numerator show up in your C matrix. And then finally, we are left with the A matrix. To build the A matrix, we're going to first kind of block off that last row and then this first column. Okay, so in this bottom row, I'm going to have the terms here from my denominator, but they're going to show up with minus signs. So it's going to be minus A0, minus A1, minus A2, and minus A3. Minus A0, minus A1, minus A2, minus A3. And then for the rest of it here, this vertical is going to be all zeros. And finally, I'm left here with this block that is 3 by 3. It's 3 by 3 since my original was 4 by 4. But in general, this is going to be a block that's n minus 1 times n minus 1. And this block is going to be an identity matrix. So identity matrix, remember, it's going to be ones across the diagonal and zeros elsewhere. So we're going to do 1, 1, 1, and then zeros elsewhere. Okay, so together these two make up my, that right there is my state space in canonical form. And so that's really great in that we took a transfer function right up here, which was a ratio of a couple of polynomials, and we were able to build an ABCD that corresponded to it. Once we've got it in this form, as we'll see later in the semester, there's actually quite a few techniques that we can do with ABCD notation that we cannot do with transfer functions. So you're like, that's great. The only challenge here, however, is that these, you might be asking yourself, well, this ABCD, it's usually all about this x1, x2, x3, x4 and how they evolve. And here we kind of just pulled it out of, pulled it like from our sleeves, like, oh, we're calling these the states. So this might not necessarily correspond to those internal quantities that you really want to measure. So we did an example where this was, it was a current and a voltage, or this was position and velocity and so on. Here, your x1, x2, x3, x4, they may or may not correspond to those physical quantities that you're very interested in measuring. So you got a relationship here that works, and you do have a nice relationship for y of t. However, in terms of that physical significance, it might not be that you're that interested in tracking the evolution of these. So that's the disadvantage of this canonical form. It kind of leaves you with something that works really nicely mathematically, and from which you can apply some techniques, but it might not be as true, or let's say, no, it is true, but it might not be as directly like just organic and useful as if you had done the state space right off the bat and you had said, my x1 is a voltage in the capacitor, x2 is current in the inductor, x3 is this other thing, x4 is this other thing. So this kind of gives you with things that work out mathematically, but they might not be such tangible physical quantities here. So there we go. But we've got a method right there that works. And so now we've got the other direction. So we have transfer function to state space and state space to transfer function in our wheelhouse. Great. So let me know if there's any questions with this stuff so far. So feel free to type into the chat if there's anything that's confusing or you'd like me to go over again. Now, we've seen, I mean, there's a close relationship between these two forms, even though they look so different. And so let's keep exploring. So are there other relationships? Are there other relationships between those two ways of representing systems, between TF and SS? Are there other relationships between transfer function and state space? And well, I guess like if I'm asking this, you might think, well, of course there is. Otherwise, he would not be writing this heading. So yes, one of the big ones is stability. So there's and this isn't the only thing, but this is stability. You guys remember is one of the most important things. If a system is unstable, we know it's gonna basically break on us. So stability can be looked at from multiple ways. So stability, I'm going to, and in particular here in this course, we're going to study two different ways of looking at stability. So one of them we already know about, which is Bibo stability. So Bibo was bounded input, bounded output. So this was an input output type of stability. And if you guys recall, we could do that based on the transfer function, right? So off of your transfer function, you could look at the poles of the transfer function, make sure that they're all on the left-hand side. And then you're like, okay, that's Bibo stability. And makes sense, right? Because transfer function is an input-output relationship. And here I've got input-output stability. Now we've got this, this state space form that also has internal information about the system. So we might think, there might be a definition of stability associated with state space that also carries some information about how the system's evolving internally. So there is, and it's called asymptotic stability. So it's a slightly different way of defining stability, and we'll explore this in a second. But again, this one was input output. This is going to be more of like an internal definition. Okay. So just as a quick reminder, so I'll say here, recall for Bibo stability. The concept was that a system was going to be Bibo stable if for a bounded input, you could guarantee that the output was going to be bounded. So basically, if your output was not going to blow up, provided that your input was in turn not blowing up. So if your input was bounded, can I guarantee an output that's bounded? And so what we would do is we would check the poles of the transfer function. Check the poles of the transfer function. Okay. And basically, we would say that a system is Bibo stable. I'll say if and only if the poles are on the left-hand side. So like the real part of the poles is negative, right? And we remember that when they were on the axis, so I'm not going to write all like what happened on the axis, but you either had that marginal stability. If they repeated, you would have instability from back in signals and systems. But basically, you needed everything to be on the left-hand side for Bibo stability as far as the poles of your transfer function. Okay, so that's nothing new. Now for asymptotic stability, this is, again, it's another way of defining stability. Before, we defined it in terms of inputs and outputs. Here, asymptotic stability is basically about my states. So about those internal states and how they evolve. And the question is, asymptotic stability will tell me, let's say do states, let's say go down to, let's say go down to 0 on their own. So the states go down to 0 on their own. That's the sort of intuitive way of understanding asymptotic stability. This means that as long as I leave the system alone, does it just kind of quiet down and do all those internal quantities go down to 0 on their own, or not, right? Like if a system internally is gonna have like something going that even without an input. So when I say on their own, this means without an external input. So can I guarantee here? Can I guarantee here that that basically, that my states are going to quiet down, provided that we've got no external input. So that's going to be what the way we're going to look at asymptotic stability. Okay, so
I have a question.
yes.
So is that like saying like in the sense of an electrical circuit, like if you have like capacitors, like you're pretty much then guaranteeing that your capacitors will be discharged after a certain period of time versus holding a charge?
Right. Yeah, so if exactly, if left to your own devices without adding any power, if things are like if the quantities are going down to 0, so that's a good example. So that's going to be, and again, and this is, by the way, this is not the only definition of stability, but this is a pretty useful one of looking at those internal quantities and saying, okay, provided that I'm not adding external force or external energy, can I guarantee that those states are going to quiet down? So indeed, so this is going to be essentially, it's going to be for a system, and you can think of it of the form x dot equals a times x. So without the external input for a system, x dot equals a times x, and and I'll say with a certain initial x0. Okay, so basically for this situation where you got x dot equals ax and some initial condition, what I'm asking myself is, does x of t go to 0 as t goes to infinity? Okay, so this means that internally my system then is kind of quieting down of its own, that it's as Quinn mentioned that example. It's a really good example of those physical quantities just kind of just discharging on their own, provided that I'm not adding any external, in that case, external voltages and so on. So as you might guess, this is, it's a slightly different way of viewing things, but there's going to be a close relationship between these two. So for this one, just as before, we would check the poles of the transfer function and make sure that here that they were on the left-hand side. Here, what we're going to do is, I'll say that for, let's say a system is asymptotically stable. So if and only if, so rather than check the poles of the transfer function, where we're going to look is at the A matrix and check the eigenvalues of A. So check the eigenvalues of A. And what we want is them to be also on the left-hand side. So let's do if and only if the real part of the eigenvalues of A is less than 0. So kind of, again, pretty similar to what we did with the poles of the transfer function. Here we are checking that matrix A and seeing, okay, what are the eigenvalues of A? Then take the real part of that. That means to say, you know, just, yeah, so look at the real part, and is the real part negative? That, and again, this corresponds to the left half plane. All right, so that's the other type of stability. So again, and we can see, and we'll be able to see that that there's going to be a relationship between these two. So again, this is all about input output. This is all about all those internal variables going down on their own. So just I'm curious. Type into the chat, which one do you think is like a stronger condition? Like if you wanted a system where you're like, oh, that's definitely stable, and you want it to be like more demanding and more rigorous, which one would you assume? And you know, so you might be right, you might be wrong, it's okay, but I just want to get a feel. So type into the chat, what do you think is probably like the stronger condition? If you're like, you know what, I really want to make sure this is definitely stable. Would you go asymptotic or would you go BIBO? Like, which one do you think is probably the one you really want to check? So I've got Paulo, Nick, and Ned all agreeing, and Hunter as well, that asymptotic is going to be the stronger condition. Yeah, so I'll ask you, like one of you, to unmute yourselves. Ned Castley, tell me, like, why do you think asymptotic?
I don't know. I kind of was just thinking like the hard cutoff at 0, like BIBO stable is just like the poles, and this is like a hard boundary, you know, like with tangents and stuff. Like you have the hard boundary cutoff.
Yeah, and here we're requiring everything to go down to 0, not just to not blow up, right? But we're tracking all these internal variables and all of them to say, you know what, we want them to actually quiet down all the way on their own. Indeed, and here we've got a number of, even though I'm just calling it X, this could be X1, X2, X3, X4. So we're demanding that all those internal variables go down to 0 on their own. So yeah, I would agree. Asymptotic stability going to be a more rigorous version of stability than BIBO. So you might think back to some an example I think we did back in Signals and Systems, where there was a system that looked BIBO, but once you looked at what was going on internally, there was actually internal signals that were problematic and that were blowing up on you. So this is definitely going to be the more demanding. And in fact, I'll tell you right now that asymptotic stability, if a system is asymptotically stable, so asymptotic stability is going to imply BIBO stability. All right, so indeed, asymptotic is the more rigorous one. And so if you guarantee that a system's asymptotically stable, you can guarantee that for sure it's also BIBO stable. Now, in the other direction, might not be true. So if you try to do this, I'll say this is not always true. Sometimes it is. Sometimes there might be some situations where a system is both, where BIBO, you know, indeed is where they're going to match up. But in general, because this is less demanding, you cannot guarantee that a system being BIBO is also going to be asymptotic in terms of its stability. But yeah, but you guys' intuition is absolutely right on why this is the case, this one being more demanding than this one. Okay. So let's do some examples with this and just get more comfortable with that relationship. So let's do an example here. So first, let's say that I've got this system, h of s equals, and let's say it's s plus 1 over s plus 2. S plus 3. Okay. And I'll ask you two questions. So part A, is the system Bibo stable? And B, is the system asymptotically stable? So try part A, and then we'll check in after you've got part A. If you feel like you've got an answer for part A that you're satisfied with, feel free to type it into the chat. And part A should be relatively quick. You can always type to your buddy real quick if you're shy about typing to the whole group. But I think this is one that honestly, yeah, you should be able to figure out pretty quick. So Hunter Baudet tells me that it is indeed Bibo stable. Hunter, tell me why that's the case.
So for it to be Bibo stable, in the denominator, when you solve for the S values, they have to be less than 0. So when you solve for S in both cases, S is -2 and -3.
Exactly right. So your poles are going to be -2 and -3. Because of this, we know that so the real part of the poles is, they're real, but it's going to be -2, -3 is indeed less than 0, right? And therefore, system is Bibo stable. Great. So we're good with Bibo stability. Now, as we talked about before, just because it's Bibo, we can't guarantee that it's asymptotic. So if we had done it the other way and we're like, oh, it's asymptotic stability, we're like, just because of that, I can guarantee Bibo stability in this direction. Not necessarily, maybe, maybe not. So let's check out part B, where we actually need to look for asymptotic stability. Now, notice that asymptotic stability, if you go back to the definition that we wrote, it's all based on that A matrix, right? So it's all based on that A matrix. Here I'm given the transfer function, so I need to find that A, B, C, D description first. So I need to take this transfer function, go from transfer function to state space, so as to build that A, B, C, D. And we're just going to need the A matrix for now, but let's go ahead and build that A, B, C, D. So I'll let you do that. I'll let you, so for B, for asymptotic stability, I'll say first, we need that state space realization. So we need that state space, that A, B, C, D. That A, B, C, D representation. So go ahead and try it on your own. You can look back at how we built it based on our example. We did one that was order 4. This one's just order 2. So it should be a little bit quicker, but I'll let you try it out. I'll give you the hint if you're a little bit confused on how to get started. First thing you probably want to do, you want to multiply out that denominator. So if you haven't done that, make sure that you do that just to get you started. So h of s, we want things polynomial over polynomial. So it's going to be s plus 1. And then you would multiply out and get s squared plus 5s plus 6 here at the bottom. Okay. And folks, let me interrupt you real quick, but what size are you making that that A by A matrix, for example? A by A, yeah, your A matrix. What dimensions would that need to be given this transfer function?
2 by 2.
2 by 2. Yep, great. So Nick agrees. 2 by 2. So and yeah, so Hunter and Nick are on the same page. Notice that this highest exponent in the denominator is 2, therefore the whole system's of order 2. So indeed, I could say, well, here my x1 and x2 dot, and just call it that. And we need a 2 by 2 matrix. 2 by 2 matrix for matrix A. Then I got x1 and x2. Then a column that's 2 by 1 right there. And then R. And then Y. And then 1 by 2, x1 and x2. And if you remember here, we've got our D matrix, but the D matrix is going to be 0, so I'm not even going to bother writing it. Okay, so let's go through this together. How about, and again, either unmute or type into the chat, what would be this B matrix right here? This B matrix, what would that look like?
0 and then 1.
0, 1, great. So we know it's always the case that it's going to be all zeros and then a 1. In this particular case, just, just 0 and then 1, great. How about down here, the C matrix? What did you guys get for that? Remember, that one was going to be based off of the coefficients of the numerator. So Paulo says 1, 1. Indeed, it's going to be 1, 1, because basically, even though we have s plus 1, it's basically, let's say we had like 1 s plus 1. Same thing. So 1, 1. Exactly right. All right. So, yeah, there we go. Jackson says 1, 1 as well. All right. Okay, and now let's get into the A matrix. So for my A matrix, remember we would have those terms right here, the ones from my denominator, but showing up with a minus, right? So here I have these guys right here, but they show up with a minus. And remember also the order, so just be careful about that. So type into the chat what I would see here and here at the bottom line. Minus 6, minus 5, great. Awesome. And we said that in terms of what remains, over here, this was going to be a column of all zeros. It's a very short column with only 1 0. And then this part over here was going to be an identity matrix. In this case, it's just a 1 by 1 identity matrix, so it's just the number 1. So you end up with that. So that's your A, B, C, D for this one. And we know this right here is our A matrix. So now we check those eigenvalues of A. to determine stability. So if you want to take this and put it into Wolfram, you can do that. As a reminder, in terms of how we did this by hand, just to give you a reminder, we would look at the determinant of lambda I minus a. Okay. And so we would do the determinant of, so lambda I is going to be lambda 0, 0 minus a, which is this 0, 1, -6, -5. Okay. So again, this is stuff that you guys have seen in your math classes before. But yeah, you would do this, and so you would do, okay, determinant of, and so you end up with a lambda. Then in the other one, it's going to be lambda plus 5 down here. Then 6 over here and -1. Okay. And so you would do this times this minus this times this, and you end up with lambda squared plus 5 lambda, then minus -6 or plus 6. Okay, and you would set that equal to 0. From there, you get your lambda 1 and 2. So you would factor that out. And what did you get there as your eigenvalues? Type those in there. -2, -3, I see from Nick and from Nico. So indeed, -2 and -3. Great. So from here, if they are both negative, then we can say that yes, system is definitely asymptotically stable. So that's great. We are asymptotically stable. What else do you notice for this example that might
The
jump
same as
out?
the poles.
Say that again, I'm sorry.
It's the same as the poles.
Exactly. So I'll say notice. So notice here, let's say the poles and the eigenvalues. So I'm going to call them the pi and the lambda I matched. So basically here in this one, the poles and the poles of the transfer function and the eigenvalues of the A matrix happen to be exactly the same, and they matched. So we're like, okay, there's definitely seems to be a pretty close relationship between that transfer function and especially that A matrix. We had said, however, that asymptotic stability was a more rigorous definition. So we kind of expect that this is not going to be the case all the time. So I'll say here, like in this case, this worked, but it's not going to be the case all the time. So sometimes they'll match up and sometimes not. But there's definitely a close relationship there. All right. So let's do another example. Let's try one here. Let's say I've got a system now given in this form. So let's say I've got x dot equals, and it's 0, 1, 1, 0 times x1, x2. Oops. Yeah, so let's, I'll just call it here on the left, x1 and x2 dot equal 1. So 0, 1, 1, 0 times x1, x2. And then plus 0, 1, r. And then y is going to be equal to negative 1, 1, x1 and x2, plus 0, r. So that's my definition right there. Okay, so let's do them in another order. So let's say A is the system asymptotically stable. And B is the system Vivo stable. Okay. So let's go through this together. So part A, asymptotic stability. What do we do? Well, we check those eigenvalues, right? So part A is asymptotic stability. So let's check that. So remember asymptotic stability, we would check the eigenvalues of that A matrix. In this case, the A matrix is 0, 1, 1, 0. So I would do determinant of lambda I minus A. Okay, so this is determinant of lambda, lambda, 0, 0, minus this A matrix, 0, 1, 1, 0. And I get what? I get determinant of lambda, then lambda minus 1, minus 1. Okay. So if I do this by this minus it by this, I get lambda squared minus 1. So solving that, I do this equal to 0. And from there, I get my lambda 1 and lambda 2. And notice, basically, I get lambda squared equal 1. So lambda 1 and 2 are going to be negative 1 and 1. Right? So if this is the case, is the system Vivo stable?
No.
It is not, right? So I'm sorry, asymptotically. So not Vivo, asymptotic. So this is not asymptotically stable. Again, these would both need to be negative, and because of this guy right here, that's problematic. So this is not asymptotically stable. Indeed. So right off the bat, this is not asymptotically stable. Now let's check whether it's Vivo stable, because we know that asymptotically is kind of a more rigorous condition. So something may not be asymptotically, but may be Vivo. So let's check out for Vivo stability. So for that one, we would check the transfer function. So I'm given A, B, C, D right there. So A, B, C, D. So I will, I'll go through this process and say the transfer function, let's call it H of S, is C Si minus A inverse B plus D. In this case, D was 0, so it's just that. I'll show you what I've got here in my notes. So the C matrix was -1, 1. Then SI minus A inverse. So this is going to be the inverse of SI minus A. SI minus A is actually going to be this thing right here. So S minus 1 minus 1. And then B is 0, 1. Okay. So I'll apply my little formula right here for this one. So it's going to be -1, 1. Then 1 over the determinant, which is S squared minus 1. And then here we switch these two and change the sign of these two. So I get S, 1, 1, and 0, 1. Okay, so that's CSI minus A inverse B. Now I'll multiply these two. So basically it's this row times this column, this row times this column. So this is -1, 1, S squared minus 1. And then with these, I'm going to get 1S. Do this times this, and then this times this. Okay. Now I multiply this row and this column. And so I am going to get right here -1 plus S, which is another way to say it is S minus 1 over S squared minus 1. Right, so that ends up being my transfer function, but watch out, because down below S squared minus 1, this is S minus 1, S plus 1. Right, and so I can wipe out these guys right here. And I end up with a transfer function of 1 over S plus 1. Therefore, the poles, I just end up with one pole. So Pi equal -1, right? So I just end up with this one pole. The only pole that I have is negative. Therefore, my system is indeed Bibo stable. Okay. So this is one of those cases where it was not asymptotically stable, not asymptotically stable, but it was Bibo stable. So as we can see, Bibo stable is less rigorous than asymptotically, as in this case. Now, in this case, they didn't quite match, right? So before we had those poles of your transfer function matching up with those eigenvalues of A. Here, we had the pole of the transfer function, we just had the 1. Interestingly, it matched up with one of the eigenvalues of A. So I'll say in general, and this is true for all cases, you can say that the poles of transfer function, the poles of the transfer function are a subset of the eigenvalues of A. So the poles of transfer function are a subset of the eigenvalues of A. Sometimes they match up. So sometimes the sets do match up entirely, but not all the time. So you cannot guarantee that they're right equal to each other. So there's going to be certain conditions for which they do. The two are going to be equivalent sets. Okay, folks, and that's the last bit of theory that we have here for chapter 3. Admittedly, yeah, I guess I was gonna say it took me a little bit longer to get through, but it's all good. Like I think we went through some good examples, and hopefully this will be yeah, prepare you pretty well for feeling comfortable with this material. So I'll go ahead and pause the report.